Welcome to a lecture on numerical acoustics. My name's Bill Anderson, and I'm a professor of aerospace engineering at the University of Michigan. My background has been in structural dynamics, including flutter, which is aeroelasticity, and involves the fluid flow over elastic bodies. It's somewhat of a related field to numerical acoustics in that I've spent my life doing numerical methods on various vibrating bodies, and of course that's a typical source of acoustic noise, so it's a rather natural progression now to move into the area of acoustics. Acoustics is really becoming important to the average engineer and scientist. There's so many situations where you need to understand sound, its generation, its propagation, and its reception by human ears. The first lecture that I'll give is a little bit detailed in that there are a lot of topics illustrated on this introductory page. I'll give a little bit on the history of acoustics. I'll follow with the idea of how sound is generated, propagated, and received. Then I'll do a little bit of the background on what sound waves are. For instance, sound waves are compressional waves. They're represented by a scalar field, unlike the electromagnetic waves, which can be polarized and are more complicated. Those are transverse waves. So sound waves are compressions and rarefactions that progress along a line, and in that sense are like axial vibrations of a rod rather than lateral vibrations of a rod, if I use a structural equivalent. I will talk about some theoretical things that I've been aware of in the past, such as the pressure on a piston face and the linear piston theory. Then I'll try to do some slides that are on gross comparisons between acoustics and some other fields that are fluid fields, such as hydrodynamics, wing theory, and then the piston theory. Before I do that first introductory slide, though, I'm going to say a little bit about my own background and my own professional career. I graduated from Caltech July of 1962 with a degree in aeronautics. I was in the aeroelasticity group, which is basically more embedded in structural mechanics than fluids. Typically, unsteady aerodynamics has been studied that way, surprisingly, in groups that are not the conventional fluid mechanics groups. From that standpoint, my fluids background is a little different and maybe a little more elementary than many fluids people that would be viewing this set of lectures. That might be good for you because I'm going to approach the material as a novice from the fluid standpoint, and so hopefully can bring a wide variety of people up to some level of understanding on what the numerical acoustics means and the equations on which it's based. I spent 3 years at Wright-Patterson Air Force Base in Ohio, worked on aeroelasticity, wind tunnel flow over wavy walls. Then I came to the University of Michigan in 1965, and I've been here since. So I'm currently completing my 30th year at the University of Michigan. About 12 years ago, I founded a consulting company, Automated Analysis Corporation, and this has been the focus of my professional life recently in terms of consultation and going into some new ventures. The multimedia discs that you are viewing here have been created under the sponsorship of Automated Analysis. Probably the greatest researcher of all times in acoustics was Lord Rayleigh. His real name was John William Strutt, and he inherited his title from his father. This was a good thing for him. It gave him enough wealth to pursue his interest in acoustics. One story is that he did a good part of his serious work when he was floating down the Nile on a barge after recovering from some malady of the time, and was able with the peace and quiet to get a lot of work done. He published The Theory of Sound, which is considered the greatest work in acoustics, back in 1877. So it's a little bit humbling to see that so much of the theory of acoustics was understood by someone more than a century ago. Acoustics is basically divided into 3 physical phenomena. The first is the production of sound, And here I'm illustrating a solid body that is vibrating and sending out noise. This production of sound could equally well be done by instabilities in fluids, such as boundary layer noise or instability in turbulent jets. And that particular specialty area is called aeroacoustics. We won't really get into that much. Rather, we're going to think of the production of sound as occurring off of typically a wall that is having a certain velocity or a known pressure distribution on a surface. The aeroacoustic problem could be considered here in the sense that if it could be converted into a proper boundary condition for our field equation, then we can handle it, and that is possible in a number of cases. But the actual generation of sound within fluids by instabilities is a very, very difficult topic right now. Once the sound is generated either by a mechanical solid source or by some fluid oscillation, then it propagates through the open medium. The most typical media, of course, are air or water. The study that we do in our numerical acoustics is primarily then to look at the propagation of this sound as it moves in space and to observe how it interacts with boundaries and with obstacles. At times we have closed cavities and we're interested in the normal modes of the closed cavities. The interaction at those walls and with bodies is important. An important concept there is the so-called impedance of the surface that it is coming in contact with. And so there are sound-absorbing surfaces, there are sound-reflecting surfaces. Those are considered boundary conditions in our field problem. The field equation is now called the Helmholtz equation. Finally, this sound is received by a human ear, and there's quite a physiological component here in terms of what the human perceives to be good noise, bad noise, and friendly, unfriendly, and so on. This has to do with details of the frequency range, the intensity of the sound, and the quality in sort of physiological senses. So we still today are learning what it means for the ear to receive sound and either be pleased or disappointed in it. Now let's look at the production of sound as generally produced by solid bodies in this case. We'll concentrate on that rather than aeroacoustics. And I'll follow a historical introduction done in the theory of sound. You can look that up. It's a very interesting reading, and I'll give the reference on our title page. Pythagoras, back in the 6th century BC, understood that if you had a stretched string and you plucked it, that the shorter strings would give a higher pitch. And so probably at that time they didn't understand the concept of tension in the string also affecting things, and that was uncovered later on. But certainly Pythagoras got the right idea some 2,600 years ago. Mersenne, French person, understood the frequencies of strings, including the effect of tension, and so this was some good 2,200 years later. So people were probably playing musical instruments all during that time, lyres and violins and so on, and were just barely able to understand the cause and effect. Now, I presume that the good violin makers really knew this instinctively and did the right thing, of course. But Mersenne found a simple mathematical relation. Galileo, who has been known for a number of things, celestial observations and so on, often stemming from his ability to make magnifying glasses, used such an instrument to look at the effect on steel when someone had hammered a chisel and on that steel, and he heard this vibrating note and realized there was something musical about it. And you may have heard that yourself if you hear people pounding on steel in one way or another, more than the ring of the blacksmith's hammer. But if the blacksmith has a chisel, you get a kind of a clear ringing note. And Galileo looked at that and saw small serrated riffles in the steel, and he was able to relate then the frequency of vibration with those wavelengths carved into the steel. I think in modern times something like the squeal of brakes on a heavy bus going by might be a comparable modern phenomenon. Bernoulli, 1755, understood how sound was a superposition of small oscillations at different frequencies. He really understood completely this process so much that it's a wonder we don't call these series of sine functions to be Bernoulli's series. But Fourier came along a little bit later and did a little better mathematical job on it, and so today we really talk about Fourier series when we speak about superposition of multiple sine waves adding up to some sort of a sensible, that is, an observable result. A major step forward in the understanding of the production of sound occurred in the 1700s and 1800s as the mathematicians and physicists learned to study the vibration of bars and plates. Plates are a very efficient generator of sound because they have a broad surface to move air as they vibrate laterally. Euler and Bernoulli, more than 200 years ago, understood the vibration of bars, the lateral vibration. The theory today is still known as Euler-Bernoulli beam theory, and I teach it almost every day at the university. Lagrange found theoretical frequencies for the cavity of an organ pipe, often open at one end. Chladni was able to visualize the stationary lines on a vibrating plate-like body by using cork dust, which would migrate to the stationary portions of the plate. I've done this myself with salt on a black background, and it works beautifully. I will often call this line a Chladni nodal line to distinguish it from the nodes that we speak of in finite elements. Sophie Saint-Germain was a noted French physicist. In response to a competition by Napoleon, she developed the fourth-order differential equations for plate vibration. Napoleon was very interested in building good plate-like structures and was interested in the vibration of bridges and other military necessities. But Saint-Germain worked from equilibrium ideas and didn't come up with quite the right boundary conditions, which was left for Kirchhoff at a little later time using the calculus of variations and energy ideas, and found the proper plate boundary conditions, which are not trivial for the free edge. Poisson solved the membrane vibration problem, and Klebisch worked with the circular membrane, and that's of course still important today in various sound generation situations. I guess a kettle drum would be a typical circular membrane that is rather pleasing to hear. Let's now look at the propagation of sound. This is our major topic of interest in this lecture series. If we go back historically to the days of Aristotle, it was thought that the air had to move in order to allow the sound to travel from a sender to a receiver. Gassendi in 1635 decided that this was true as well, and proposed that there was a fine stream of particles that had to move through the air in order to hear it. That was not true, of course, but in modern times we can't be too critical because it turns out that is the way that light travels, through small packets of energy called photons that really do go from the light source to the light receiver. Gassendi did correctly realize, though, that the speed of sound was not a function of the tone, that is, the frequency of sound. Early experiments had to do with shooting of cannons and flashing lights and measuring the travel of sound over relatively large distances so that the inaccuracies in their measuring equipment didn't dominate the resulting speed. They got a value of 350 meters per second, which is not that far off from modern values used, such as 343 meters per second at room temperature. Boyle in 1660 observed that the medium, say air, was necessary to transport the sound, and he did it by putting an alarm clock in a vacuum bell. Then he evacuated the air from the bell and let the alarm clock ring. He had a false start on this, apparently, where at first he had the alarm clock sitting on the bottom of the vacuum bell, and the sound was still heard through the structural path. Then later he realized he had to isolate the alarm clock and get it up in the air on suitable foam or whatever. And then he found indeed the alarm clock couldn't be heard. So that was quite a step forward. Von Guericke, 1686, doubted that the air had to move in the large as a stream of air. And so he was on the right track. Another measurement of the speed of sound was done by the Academy of Science in Paris, 1738, and they got a little lower number, which was probably more accurate considering the temperature that they were measuring it at. Most of these experiments had to do with a loud noise like a cannon or a gun, and then a flash of light, and basically assuming that the speed of light is infinite, they were able to find the time duration of the sound impulse from point A to point B, and they did it over rather long distances because of the lack of accurate time measuring devices. Laplace was the first person to understand that the propagation of sound waves through a medium is adiabatic. Now that means that there's not heat conduction taking place along the wavelength such that you can equalize the hot and cold temperatures. You see, where the fluid is compressed, it would naturally be warmer. Where it was expanded, it would be naturally cooler. The question is, if the process was slow enough in some sense, or the wavelengths were short enough to allow shorter conduction paths, then maybe the propagation would occur at a constant temperature. It's found that that's not true. I'll talk about that later, and it has more to do with the wavelengths, that there's even low frequencies have such long wavelengths that it's too large a distance for the temperature to equalize. He also came up with the speed of sound then as square root of gamma RT, so we see that temperature is the driving parameter behind the speed of sound. Now let's go on to the reception of sound, which I've said is more of a physiological thing. People have always been interested in that because of deafness of humans. And some of the early studies did revolve about that sort of concern. Kircher in 1650 realized that if you took a megaphone and stuck it in your ear, it acted as an amplifier of sound, and you had a hearing trumpet. Makes you wonder if there wasn't somebody in some military marching band that didn't do the same thing at some point and stick his trumpet in his ear and realize he could hear the enemy talking or something like this. Savart, very famous person in fluid mechanics, tried to determine the range of audibility for humans and came up with numbers that are a little bit too broad, saying that humans can hear from 8 to 24,000 hertz. Not true. Humans really can't get down much below 15, and on the top end, much above 15,000. The television screech is somewhere around 16,000. It has to do with the horizontal signal as it's displayed on the screen, and then the electronics that drive that. That used to really be hard on me when I was younger because I could hear that frequency, and sometimes I literally couldn't be in the same room as poorly made television sets. That's one of the advantages of advancing age. You lose that ability. You can't hear that TV squeal as you get older. Now, this group of fellows, very famous fellows, decided that the audible range at the lower end was more 16 to 32 hertz. And so you see, depending how they did their measurements, they're human subjects, and depending how they measured frequency, they were getting slightly different results. The next figure continues this historical review about reception. Topler, Boltzmann, and Rowley were all interested in the minimum audible amplitude, and we're going to show you the full range of human hearing in a few slides later. So these people were interested in the lower boundary of such a figure where if you plot frequency on the horizontal axis and some sound level, say in decibels, on the vertical axis, then there is a curve here above which sound pressure levels must exist in order for humans to hear it. Ohm developed his law of audition, and for the reception of sound, this would be comparable to Bernoulli's ideas about the creation of sound and the superposition, and Fourier's ideas about heat conduction and how you can break temperature fields into these harmonic functions. Upham got into architectural acoustics, and these last three have to do with that. It's been known for a long time that large buildings have special problems. It involves a lot of reflection of sound. Today, these problems are generally handled by methods called ray tracing, and rather than solving the field equation such as we will do. The reason is there's so much detail in a large auditorium with so many seats and wall conditions and nooks and crannies that it's difficult to do a full field solution. It would be too expensive. Henry has carried this further into qualitative understanding, and Sabine into the quantitative logic. But, you know, even today, large auditoria are constructed and found to have very poor qualities in terms of music productions. We find that in Detroit there was an auditorium made in recent times that had to be retrofitted at great expense to try to make it musically okay. Yeah, I think even just to reach an okay level. So obviously the acoustics of large auditoria are not fully technically handled right now. Let's talk a bit now about the more physical nature of acoustic waves. Sound waves are traveling waves. They're harmonic oscillations of the various parameters, pressure, temperature, density, in a medium. And so sound tends to move along a straight line unless it's affected by one of these processes below here. But generally speaking, propagates along a straight line and is a succession of compressions and rarefactions and more compressions and so on. But these points tend to move. And there is a wave velocity that's associated with that pressure disturbance. Often pressure is viewed as the driving quantity. In fact, we're going to find in our field equations ultimately that you generally try to eliminate temperature and density variations in terms of pressure. So if you do use what are sometimes called primitive variables, the true physical variables, rather than potential functions and so on, you find that pressure is usually the variable that's used to characterize the sound field. Now, you probably have a feeling for reflection off of a wall. If it were a perfectly reflecting hard wall, then you'd get the energy bounce back again. At the other extreme, you have absorption, and that would be where a sound wave in principle might come into a wall and not be reflected at all. So that would be a perfect absorber. Then these intermediate terms have to do with interaction between a wave and a body, or in the case of interference, you've got the interaction between two waves. I won't go into these in detail. I think I would refer you to the book by Leo Beranek, and I'll give on the title page, I'll give that as a reference. One thing that's kind of interesting is that the sound waves can't be polarized. You know how that's done with light waves. For instance, when you wear polarized glasses at the beach, you want to have a vertical plane of polarization so that you don't get the horizontal waves coming through. And sound cannot be polarized in that way. Sound is a compressional wave and not a lateral wave. But of course, various electromagnetic waves, not only light, but other such waves, microwaves, and so on, are polarizable. I'd like to make some comments about some of the practical side of sound and how you might measure the intensity of sound. We can characterize sound waves by the wave speed, the wavelength, the frequency, and the amplitude. And there are relations, of course, between the wave speed, the length, and the frequency because of the constant speed of sound. The amplitude is a very important measure. This could be measured typically as a pressure amplitude, and there are a number of different ways to measure it and interpret the sound level. First of all, I want to repeat that idea that your ear is quite adept at hearing pressure waves that are less than 1,000th of an atmosphere, and that means that the linear theories really do apply. It makes it somewhat reminiscent of linear elasticity or the infinitesimal elasticity theories, which are quite accurate for solid bodies. And the same thing is true here, that the differential equation therefore, that applies to acoustics, which is the Helmholtz equation, is really rather accurate. And the problem is not so much in the field equation, but rather putting the proper boundary conditions on and other sorts of constraints. Now, I'll go through some of the ways that we can measure the sound amplitude on the following slides. One of the most commonly used measurements for sound intensity is the sound pressure level. This is a logarithmic ratio of pressures and has a 20 out front, and the log to the base 10 is used. The reference pressure is quite small. Indeed, for air, it's only 20 micropascals. Pierce mentions in his book that in liquids it's common to use 1 micropascal as the reference pressure. The range of audibility for humans is really broad. It's something that's astounding, in fact, and that's what requires this logarithmic scale. Humans' audibility range goes from 0 decibels up to 130 or so, where it becomes painful. The pressures involved, therefore, range from the reference pressure, where the logarithm is 0, of 20 micropascals, up to the 130 decibel level, where I've calculated that that is less than 1,000th of an atmosphere in terms of the RMS oscillating pressure. So isn't it interesting that your ear is so sensitive that it can hear noises that are 1,000th or 1,000,000th of an atmosphere oscillating? And even when you get up to 1,000th, then you're overloading the system badly. So sound certainly is a linear process in that sense. It's a very small perturbation on a rather large mean value of pressure. Sound intensity is another way to look at the sound in terms of a energy basis, and this has to do with the rate at which sound is transmitted through a unit area, and it's given in this form. So the dimensions are energy per unit area. Here I'm showing units of watts per meter squared. So I'll continue on the next figure on more measures of sound level. This sound energy density, we'll call D, and that's the energy per unit volume of a medium, and again can be expressed in terms of pressure and the ratio of specific heats here. For a diatomic gas, which air is largely, 1.4 is the proper value. I guess that's because both nitrogen and oxygen are diatomic, O2 and N2. Another idea is the total radiated power. Sometimes you take a noise source and put it in a room that's a reverberant room, which has entirely hard walls, and then you find that that noise tends to fill this space, and so it's kind of interesting then to get some measure of what the total radiated power can be. Let's consider now the audibility limits for human hearing. This is rather concisely shown on a single figure. At the lower end, we find that humans are finely tuned to hear frequency ranges in the range of the human speaking tones. So you get this very, very sensitive region where sounds even of 0 decibels are possible to be heard. It cuts out at around 15 or 16,000 hertz here, and that is an interesting high end, showing that you don't need protection, particularly against higher frequencies. At the low end, we've shown before that there are various measured limits on audibility of 15 to 20 hertz, and you can imagine then, depending on the individual that was being tested, that number would vary. At the upper end, you have the threshold of feeling, wanders somewhere around 120 decibels. The beginning of pain is somewhere around 130, and certainly very painful at 140 decibels. There's a sketch curve here suggesting that you need protection if you have long-term exposure in these frequency ranges, so various industrial processes might need that. For instance, there is a case where you have jackhammers, which might be, let's say, 100 decibel range, so people operating jackhammers probably should be wearing hearing protection. Rock concerts can get as high as 120 decibels, so they also look like a bad idea. Metal stamping plants can be as high as 90 decibels, and if you've ever been in a sheet metal stamping plant, you know how pervasive that noise really is. It's hard to concentrate or do any thinking in that much noise. Vacuum cleaners are around 80 decibels, busy traffic at 70, quiet restaurant perhaps at 50, rustling of leaves maybe at 20, and human breathing could be down as much as 10 decibels at 3 meters. I have a friend, Joe Isley, who as a young person drove a tractor a lot, and he developed a notch in his hearing ability where he couldn't hear noises over a certain range. He says now that he has trouble when he attends Shakespearean plays because he's missing some of the hissing sounds, the S's as in forsooth. And so that's kind of an interesting concept, that if you ride a tractor a lot when you're a young person, then you don't enjoy Shakespearean plays when you're a little older. When one wants a measurement of sound level, you need to think about how you might emphasize the reading when you've averaged over a broad frequency range. A purely mechanical approach might be to say that all frequency content was the same, but we know now that the human ear doesn't hear as well down at the low or at the high frequencies. Therefore, you might build in some sort of a weighting factor as a function of frequency that would emphasize the mid-frequency range that we can hear, and then de-emphasize the frequencies at the tails of our audibility. Such a figure is shown here where there are 3 proposed scales for measuring sound. The A scale is used most often in the United States with what's called fast time averaging. The B scale is another physiological scale, but the C scale is one that is flat and is just more of a cold measurement of total sound level. I have a story to tell about this, that when I was a young man, some 20 years old, so wow, this would be 37 years ago, in Dallas, Texas, I did some background sound measurements for the Vought Aircraft Company. They were going to build a wind tunnel out on a flat field behind the plant in Grand Prairie, Texas, and they wanted the background measurements to see what change the new facility would make. So I found myself one day standing with a sound meter out in the middle of this field and watching it, and the scale was, the measurement showed rather low sound level, and then all of a sudden it started kicking up. And I couldn't believe it. Quite a lot, something loud was going on, but I couldn't hear it. So obviously I was using something like a C scale in today's discussion. What I found was there was a mourning dove in a tree some couple hundred feet away, and when it cooed, it literally drove this meter berserk, and yet I could barely hear it. It was very low frequency. I think you know what a mourning dove sounds like. It's quite a low, soft sound. And so that's an example of how you might want to have a weighted scale to more reasonably represent what the human ear hears, not what the true level of sound pressure is on some absolute mechanical scale. So recommended in the U.S. is to use this A scale with what's called fast time averaging, and as you can see, basically you're penalizing the measured sound over most of this range with as much as minus 38 decibels or so, up to where you reach actually a little overshoot and you're enhancing the sound reading in this mid-frequency range. In solving practical acoustics problems, we need the concept of impedance. There are several definitions for it. Some of them are more appropriate for a discrete circuit, where you might have sound being piped around in tubes and out horns and things like that. One of the versions is more important for solving field equations, such as we're interested in. In general, impedance is a measure of the resistance the fluid offers against an imposed velocity. So it's a measure of how the fluid does not like to be pushed around. The ASA impedance is a ratio of pressure to volume flow, and that's appropriate for acoustic circuits. And typical units used are these. The specific impedance is the one that we're mostly interested in, and the ratio of pressure to velocity at a point. The specific impedance is often used to characterize the acoustic treatment on a wall, where you may have incoming sound being handled and causing pressures in a certain phase relation at a wall, which might be a partial absorber or have other characteristics. Usually the impedance is a complex number in that case. Mechanical impedance, again possibly used more for circuits, is the ratio of force on some specified area to velocity, and again useful maybe for mechanical devices. The specific impedance is our favorite impedance, and one way to use it is to characterize the fluid going out to infinity, and people talk about far field impedance. Sometimes if you do a finite mesh of a given situation, perhaps you have a body radiating sound and you'd like to terminate the mesh at some radius away from the body, you'd like to terminate the mesh and have the mesh look into the far field with a proper impedance match. That's not done a lot in acoustics. It has been done more in electromagnetics, and I got into a dissertation position once as an advisor where we did that, and questions of matching your finite field mesh to the far field really were quite important to avoid reflections and so on. So I guess there are those different usages of the impedance, both at a wall, in our case, characterizing something rather local, and then trying to match to infinity something called a far-field impedance. We'll consider the impedances in more detail now and start with the ASA impedance. It has the definition of pressure over a cross-sectional area and then a velocity. Now both the pressure and the velocity are oscillatory, of course. This turns out to be useful for branch circuits that are consisting of tubes, say, where you're piping sound around in a system. And it turns out to be useful because you can handle these impedances in a way in branch circuits that makes sense. Consider this hypothetical case where you have a tube of a given area on the left, and then it branches into two tubes, each of half the area on the right. It turns out the impedance then for the left here can be calculated as matching the impedance of these two on the right, and that would be the intent of this circuit, to have a matched impedance. The calculation on the right here actually follows the way of adding resistors in parallel. Were we adding something like a conductance, this would be straightforward in our case, but we're trying to work with impedances, and you get this more complicated formula that many of you probably remember from your electrical circuit theory. Well, this sum here, because you have half the area, but the same velocities, because by conservation of mass flow, when there's no gross area change, then the oscillatory velocity has to remain the same as you progress from left to right through the junction. Then those can be added up, and lo and behold, we do have a matched impedance case here. So this is a rather special kind of impedance. It's one that we don't really use much in our field representation of sound, however. Now let's look at specific impedance. This is a useful version to use in three-dimensional boundary value problems, such as we do in numerical acoustics. So this is the one we're interested in. It's the pressure over the velocity at a point. It's given the symbol Z sub S because of being specific impedance. The interesting thing is that it's almost the same at all points in a space. You often hear comments like far field impedance, and that would be an unbounded space going on forever, and you get a certain value. But it turns out on the face of a piston, a one-dimensional piston moving in a tube, let's say, that this turns out also to be literally true for that case. The impedance on the face of a one-dimensional piston is also this P over V, which can be shown to be rho C. And so kind of an interesting concept, and has an intrinsic meaning, and probably one of the most used ones is the impedance for the far field, which is a measure of the basic, the property of the medium itself. The third impedance was mechanical impedance, and that's good for systems that are composed of lumped devices, circuit devices. And often you know what the forces are, and you can calculate then the input of such a force, like a diaphragm in a loudspeaker system illustrated here. This is a physical diagram above here that shows the system of a tube that's open at one end, and then some driving force on a diaphragm. You might think of the driving force itself as being external to the diaphragm, and then some sort of mechanical impedance due to the diaphragm itself, which could have the capacitive, inductive, and resistive components. And then the far field out here will be felt, well, probably if you model right to the mouth here, you're going to come up with an air load impedance, and that would probably have some end correction for if it were placed right there in terms of the shape of the mouth here and whether this had some kind of a rolled edge or whatever. So in this case, we're showing a series impedance idea of the mechanical aspects of the diaphragm and then the fluid aspects of the air load out here. This time they're adding as if in series. A very important concept in acoustics is that of the pressure on a face of a piston that's moving into the medium. We'd like to look at the one-dimensional example of this, and you can reach that with two limiting cases. One is a very big piston that's moving the entire half space of the fluid medium ahead of it. Or you could take the second case would be a small piston filling a tube, and that's what I illustrate in this next figure. Here you have a piston being driven in the left end of this tube. The air, or whatever fluid medium is being compressed and expanded and so on in the length of the tube. The relevant equation is the wave equation shown here. I'm going to fully derive that later, but presently I'm just going to take about 5 figures and show how you can characterize the pressure on the face of the piston. And that's very useful later on as a reference pressure for a limiting case for a number of different theories. It turns out it's fairly valid for higher frequencies, even on three-dimensional bodies, and it's a rough cut at a lot of different pressures that you might later want to calculate. The boundary condition at the left end would be to match the velocity in the fluid field, call it at point x0 at the face of the piston. So our coordinate system starts right at the piston face here. That's going to be our x coordinate. And then we'll give it the symbol V0 to stand for the time dependence of the piston motion itself in the x direction.